Swayam Prabha. Digital India. Educated India.
Welcome to lecture 2 on stability analysis of slopes. In the previous lecture, we have introduced to stability analysis of slopes and we discussed about types of slopes and failure types, causes of slope failure and analysis of infinite slopes we just introduced. Contents of this lecture we will discuss further on analysis of infinite slopes, and thereafter we will try to look how a finite slope can be analyzed. In this slide we can see two typical types of failure for a slope. They are circular and non-circular, and there is in this slide a translational failure was shown, that is a particular type of slope failure. In case if there is a rigid stratum at a certain depth below the ground level, then the particular slope failure is said to be a compound slip or a base failure. Now let us look in detail about the analysis of infinite slopes. The assumptions involved are: soil is homogeneous, the stress and soil properties on every vertical plane are identical, on any plane parallel to the slope stresses and soil properties are identical. So, the soil properties and the stresses are same. This implies that failure in such slope takes place due to sliding of the soil mass along a plane parallel to the slope surface at a certain depth. So, here a typical cross section of an infinite slope is shown, and here is the slope surface which is inclined at an angle beta with horizontal, and this is a rigid stratum, and here with broken line the failure surface which is shown here at a depth z below the slope surface. The failure surface is parallel to the slope surface, and HW is the height of the water from the slope surface. And consider a block of width b horizontally, which is shown in this slide, and z is the depth of the block under consideration. So, this is the water table which is HW units below the slope surface. Now, let us look into the weight of the segment ABCD, where this can be given as W as the weight of the segment ABCD, gamma that is the unit weight, Z is the depth, B is the this horizontal width, and then 1 is the per meter unit length of the per meter length of the section under consideration. So, based on that the weight of the segment ABCD can be given as W is equal to gamma ZB. Tangential stress tau down the slope can be determined from the tangential force T, which is a component of weight of this segment ABCD, which is given by tau is equal to gamma ZB sin beta divided by B by cos beta, which gives rise to gamma Z sin beta cos beta. That is, tangential stress tau down the slope is tau is equal to gamma Z sin beta cos beta. Normal stress sigma within the segment is sigma is equal to similarly gamma Z cos square beta. Now, the pore water pressure U on the slip surface, that is this particular surface is here, failure surface is here, HW is the water height from the slope surface, the top surface of the water is HW units below the slope surface, hence this height is Z minus HW. So, U is equal to Z minus HW gamma W cos square beta along this surface. So, now you know the tangential stress tau and normal stress sigma within the segment and pore water pressure U on the slip surface. From this we can calculate normal effective stress sigma dash as, that is total stress minus pore water pressure. With this we will get gamma Z minus gamma W Z plus gamma W HW cos square beta. Shear strength available tau f at the base of the segment can be written as tau f is equal to C plus sigma tan phi. In case of effective strength parameters, tau f is equal to C dash plus sigma dash tan phi dash. So, factor of safety can be defined as factor of safety as tau f by tau. This tau f is the shear strength available and tau is the shear stress which is caused by the disturbing forces. So, for the general case we can write now tau f substituting sigma dash here, we will get this expression, which is factor of safety is equal to C dash plus tan phi dash into cos square beta into gamma Z minus gamma W Z plus gamma W HW divided by gamma Z sin beta cos beta. So, this is a general expression for an infinite slope stability analysis. So, let us look into different cases and we see that how the factor of safety varies. Now, considering the special cases within infinite slopes, case A is the dry cohesionless soil where C dash is equal to 0 and HW is equal to Z, that is the water level is at the failure surface, that is along the rock stratum surface at a depth Z from the top surface. In this case, if you substitute in the generalized expression whatever just we introduced with C dash is equal to 0 and Z is equal to HW, we get factor of safety is equal to tan phi dash by tan beta. This expression indicates that factor of safety of an infinite slope with a cohesionless soil with a cohesionless soil is independent of the depth of the failure plane. So, this implies that factor of safety of an infinite slope with a cohesionless soil is independent of the depth of the failure plane. So, this particular case for a critical case, a factor of safety is equal to 1 indicates that beta is equal to pi dash, that is slope inclination equal to the internal friction of the internal frictional angle of a material. So, this is actually nothing but an example of sand dunes formation in nature. So, for a critical case, if in case beta is greater than phi dash, the slope tries to fail and adjust to the angle which is that angle of repose, that is in this case phi dash will become equal to phi angle of repose. So, for a critical case a factor of safety is equal to 1. So, beta is equal to phi dash, the slope is just stable. For beta less than phi dash, that means that the driving shear stress are less than the available shear strength. Let us look this in the tau sigma plot. Let us consider a tau sigma plot which is shown here, and slope inclination is indicated with the broken line here, and more failure envelope is indicated with an yellow line which is shown here. Now, as long as beta is less than phi dash, the tau is less than tau f. The slope is said to be in stable position independent of depth of the slope. Independent of the depth of the slope is said to be stable. For case beta is equal to phi dash, just now we said that the tau is equal to tau f, that means that the slope is just stable and that r it is attaining or on the verge of the failure. When beta say greater than phi dash, if this line crosses and it is above this line, that indicates that the tau, that is driving shear stress, is more than the available shear strength. That indicates that the slope would have already failed at all depths. Suppose in case if that indication is there, that means that slope would have already failed at all depths. So, for beta less than phi dash, tau is less than tau f, the slope is said to be in stable condition independent of the depth of the slope. For beta greater than phi dash, tau is greater than tau f, slope would have already failed at all depths. In case B, let us consider saturated cohesionless slope, that is, in this case C dash is equal to 0 and HW is equal to 0. That means that water level is at the slope surface. With this case, again in the general expression, if you substitute, the factor of safety term is obtained like gamma dash, that is submerged unit weight of the soil, to into tan phi dash divided by gamma tan beta. Gamma is the bulk unit weight and beta is the slope inclination. So, this indicates that factor of safety of a saturated cohesionless slope is about half for a slope without saturation. So, that means that if a slope is there with so factor of safety of a saturated slope is saturated cohesionless soil slope is 50% of the slope without saturation, if gamma submerged by gamma is equal to approximately is 0.5. For a C phi soil with HW is equal to 0, we can write this expression factor of safety is equal to C dash plus tan phi dash cos square beta into gamma dash z divided by gamma z sin beta cos beta. So, that means that again C phi soil, but under saturated conditions at water table at the top surface, that is at the slope surface. In case C, for a C phi soil with HW is equal to 0, this is the expression we have derived. A factor of safety is equal to C dash plus tan phi dash cos square beta into gamma dash z divided by gamma z sin beta cos beta. So, assuming factor of safety is equal to 1, then this z becomes the critical height. So, that can be obtained, HC can be obtained as by rearranging this expression, we can write HC is equal to C dash secant square beta divided by gamma into tan beta minus gamma dash by gamma into tan phi dash. So, this is nothing but if you rearrange these terms, C dash by gamma HC is equal to tan beta minus gamma dash by gamma tan phi dash divided by secant square beta. This is nothing but a stability number. So, for C phi soils there is a limiting depth for stability. So, that one should be noted, for C phi soils there is a limiting depth for the stability. So, previously in this case, in the previous case where there is a frictional soil, the factor of safety expression is independent of the depth, but in this case for a C phi soil there is a limiting depth for stability. Let us consider the case C once again for a C phi soil. Now, let us consider this in tau sigma plot. Let us consider beta 1 is a certain slope inclination and beta 2 is another certain slope inclination, and this is that more Coulomb failure envelope with C is here and then phi is the angle of C dash is the this intercept is C dash and phi dash is the angle of this particular envelope. Now, for beta 1 less than phi dash, for beta 1 less than phi dash, the tau is less than tau f, that means the slope is under stable condition. Say for beta 2 greater than phi dash, for beta 2 greater than phi dash at certain depth, for this depth the slope is just stable, but here in this case the slope is under stable condition, but here for beta 2 greater than phi dash tau is equal to tau f, that is the slope is just stable condition. The depth at which tau is equal to tau f is called the critical depth HC. So, in the previous slide we have calculated. So, this is the depth we are referring, beyond which what will happen is that this indicates that the failure would have already occurred. So, here in the tau sigma plot, in the similar to in the previous slides, what we try to do is that we try to represent more failure envelope and consider soil surface with the different slope inclinations, and if you look into this here, as long as this beta 2 is equal to phi, then they can say that the slope has just attained a failure. Once beta 2 is greater than phi dash, that means here somewhere here it actually attains the tau is equal to tau f, beyond which already the slope would have already failed at all depths. Now, let us having looked into analysis of infinite slopes, now look how a finite slopes can be analyzed. So, the possible failure surfaces, if you look into it, so we discussed and we have shown also there are possible planar failure surfaces, circular failure surfaces and non-circular failure surfaces. And when these planar failure surfaces will come and when this circular failure surface will come and then non-circular failure surface can occur, let us consider. Planar failure surfaces occurs along a specific plane or weakness. So, this is in case there is a weak clay layer. So, the planar failure surface, the failure surface can take that particular path. So, planar failure surface occurs along a specific plane or weakness. Excavations into stratified deposits where the strata dipping toward the excavation. Suppose if there is a strata and if it is dipping towards the excavation, then the failure plane can be planar and can be in the direction of that weak plane. In earth dams, along sloping cores of weak material, not likely, this particular planar failure surface may not likely to occur in homogeneous soils. So, in stratified deposits or in examples like earth dams where there is a sloping core of weak material, core material which generally comprised of low strength material, but which is having an impervious characteristics. Circular failure surface, soils exhibiting cohesion C and phi and no specific planes of weakness or great strength. So, soils exhibiting C, that is cohesive slopes only, or soils exhibiting C and phi and no specific planes of weakness and great strength. So, for the soils which does not exhibit any specific planes of weakness or great strength, then these circular failures can take place. And non-circular failure surfaces, when the distribution of the shear resistance within an earth mass is non-uniform, failure can occur along surfaces more complex than a circle. So, when the distribution of shearing resistance is not uniform, then it can actually form something like a non-circular failure surface. Now, let us, in this particular slope, a slope with a cross section is shown, the cross section of a slope is shown, and here one vertical and horizontal. So, the important aspect here is that what is the safe slope for a given structure under consideration. For example, if it is an embankment which is constructed for an approach road, so what should be the a safe slope? Suppose if the cutting is made and is being made, so it has to be decided, it has to be pre-designed based on the available properties of the soils and then conditions, whether it is short term or long term conditions. We need to look into what is the safe slope which can be allowed. So, here different types of failure surfaces are depicted here. In this case, a planar failure surface which is shown. The other one here is that another possible two wedge failure surface which is shown. So, this can occur if there is a plane of weakness, and these two are circular failure surfaces which are shown here. The analysis of finite slopes, the factor of safety for finite slope depends on assumed location of the center of rotation for the slip surface. So, assumed location of the center of rotation for the slip surface and radius of the failure surface and type of failure, whether it is a toe failure, base failure and slope failure. So, the factor of safety for finite slope depends on assumed location of the center of rotation for the slip surface. There can be a number of locations of the centers and there can be number of surfaces. What we need to find out is that the surface which gives the least factor of safety has to be determined for ascertaining a slope with for ascertaining a safe slope. Radius of the failure surface and type of the failure, that is toe failure, base failure and slope failure. So, in generally, as we discussed in the previous lecture, the sections of unit width are assumed for the analysis. So, here is if the slope or a bund or a canal cut, a vertical cut is there or a cut which is shown here, and you can see that the section of unit width assumed for the analysis is considered. So, it is assumed that a unit width, the length of the length of this section is assumed as, for example, if the weight is calculated, then if the weight is calculated in meters, then we calculate the weight of this section per meter width of this particular section. So, if this is the slope, this is that section of unit width assumed for the analysis, and that is considered because this type of structures or this thing illustrates a plane strain condition. Now, let us look at different methods. The first method being circular analysis, undrained condition, or phi u is equal to 0 analysis. Analysis in terms of total stresses, this analysis in terms of total stresses and applies to short term condition for a cutting or embankment soil profile to comprise fully saturated clay. So, this particular circular analysis or undrained condition or phi u is equal to 0 analysis, this is an analysis in terms of total stresses and applies to the short term condition for a cutting or embankment assuming soil profile to comprise fully saturated clay. So, here a cross section of a slope is shown and this is the failure surface, the possible critical failure surface. R is the radius, W is the weight of the wedge, and this is determined by determining the area and per meter width of the section perpendicular to this plane of this figure, and that is area into this width into unit weight of the soil is yields to weight W, and if this resultant, if this location is shown as the CG of the entire section, if that is actually located at a d distance from the center of rotation. So, this point is the center of rotation and this is the angle theta which subtends. So, based on that the length of the circular arc can be determined. So, now if you look into it, if this is the driving this induces driving moment, and this now the resisting moment is mobilized by the shear strength which is available. In this case, for phi u is equal to 0 analysis for undrained conditions, the undrained cohesion provides, assuming that undrained cohesion which is uniform here and then have got Cu into L is the cohesive force into multiplied by R gives the resisting moment. So, factor of safety here is defined as resisting moment divided by driving moment, where resisting moment is Cu La into R and driving moment is W into D. So, the demerit of this method is that determination of W and D. So, this yields to the method of slices. What we do is that we divide this entire cross section into number of slices and determine the factor of safety. So, in this the demerit of this method is that determination of the W and D, that is the center of gravity and its location, that is the CG of the determination of the weight of the entire slope portion and its location is the demerit of this particular method. Now, let us consider similar under undrained conditions, but there is a load which is acting at the top of the slope, and let us consider how we can calculate the factor of safety. Let us assume that this is the failure surface which is given at a distance r, and W1 is the weight of the soil mass which is acting at the CG of the mass. CG of this portion is at this point and this W1 is the weight of the soil mass, and W2 is the external loading on failure area. So, that is we wanted to see what is the influence of this external loading on the stability of a slope, and this is the moment axis assumed center of rotation for failure soil mass. This is the assumed center of rotation for the failure soil mass, and this D1 is the distance of the location of W1 from center of rotation horizontally, and W2 is located at a distance D2 from the center of rotation horizontally, and tau or Cu is the shear resistance developed along the slip surface or failure surface. Now, let us look the driving moment which can be given by W1 D1 plus W2 into D2, that is moment about this point. Resting moment is now only Cu into L into R. So, factor of safety is nothing but a ratio of resting moment to driving moment, which is Cu L R divided by W1 D1 plus W2 D2. So, this in this also, even in the loads which are considered, the per meter or per unit width of the analysis is considered, and which yields factor of safety. Now, let us look another extension of this circular arc analysis for determining, and this is popularly known as Taylor's stability method or Taylor's stability charts. So, undrained analysis, Taylor's stability analysis. So, this figure which shows the nomenclature used for developing stability numbers by Taylor 1948. So, 2 theta is the angle which is indicated here, and alpha is the angle with the horizontal, that is inclination of this line with the horizontal for locating the indicating the geometry of the slope. Beta is the slope inclination, W is the weight of this portion of the slope at a distance d, which is at Cg, and dh, where d is the depth factor. So, and h is the height of the slope. So, this is the nomenclature used for developing stability numbers. Now, let us extend now based on the derivation already we have made. Factor of safety can be given as CLR divided by WD, where CLR is the resisting moment and WD is the driving moment. And this is the factor of safety, which is the lowest factor of safety obtained for the circular analysis. So, factor of safety is this factor of safety is the lowest factor of safety obtained from circular arc analysis. Now, W, the weight, is a function of unit weight, height and geometry of the failure surface, the slope inclination and other components. So, geometry of failure surface can be characterized by three angles, alpha, beta, theta. This alpha, beta, theta are shown once again. So, this is alpha, beta and theta, this is this angle. So, rewriting 1 as C divided by factor of safety is equal to CR, that is CR is nothing but required cohesion to just maintain a stable slope, and gamma H, that is this portion, into F into alpha, beta, theta. So, rewriting 1, we can get C by Fs, that is cohesion divided by Fs, which gives a value that is called CR, is the required cohesion to just maintain a stable slope, is equal to gamma H F alpha, beta, theta. Where function alpha, beta, theta is a pure number and the designated as the stability number Ns. The Taylor stability number is now indicated as Ns is equal to Cr by gamma H. The Taylor stability number N suffix S is equal to Cr by gamma H, where Cr is the required cohesion to just maintain a stable slope. Now, in this slide, the Taylor's curves are shown after Taylor 1948, where you can see here for beta greater than 53 degrees, this Taylor stability number is independent of the depth factor. So, for beta is equal to 60 degrees, 65 degrees, 70, 75, 80, 85, 90, the stability numbers are given here. For beta is equal to 90 degrees, that means that this is a vertical cut, the stability number is 0.261, which can be obtained here for beta is equal to 90 degrees. So, here different types of circles are passed, like slope circle, toe circle and base circle. The zones are indicated here. So, for this is valid for beta less than 53 degrees and the depth factor cannot be ignored, but beyond that this indicates that the depth factor will not come into picture. So, this particular curve is for phi u is equal to 0 soils, that means that these are for the undrained condition, that is Cu, that is purely cohesive soils or saturated cohesive soils. Undrained analysis stability charts, Taylor method we are discussing, and in the previous slide we discussed that for beta greater than beta less than 53 degrees, the stability number is a function of beta and d by h. That means that you have seen the stability number is varying for beta and the depth factor d. And for gentle slopes, the critical failure surface goes below the toe and always restricted above the strong layer, hence depends on its location. That means that as the failure surface cannot penetrate into the strong layer, so it restricts along the strong layer. So, the critical failure surface goes below the toe and always restricted above the strong layer, hence depends on its location. So, for this purpose the location is required. That is why for beta less than 53 degrees for gentle slopes, this is which is required for the location of the stronger layer is required. For beta greater than 53, that is stability number is a function of beta only, all critical circles pass through the toe. This is because for such steep slopes, the critical failure surface passes through the toe of the slope and does not go below the toe. So, for the slopes which are steeper, the critical failure surface passes to the toe of the slope and does not go below the toe. For a vertical cut, beta is equal to 90 degrees, let us consider ns is equal to 0.26. The short term condition, if you calculate, the critical height is obtained as hc is equal to 3.85 c by gamma. So, if you remember, we have derived the similar expression in case of for undrained conditions while discussing earth pressures, and we discussed that critical height of a vertical cut is about 4 cu by gamma. So, here we actually obtained same expression from the Taylor stability number. The position of the critical slip circle, that is for factor safety is 1, may be limited by 2 factors. So, that is the depth of the stratum in which the sliding can occur, the possible distance from the toe of the rupture surface to the toe of the slope. So, the position of the critical slip circle, the position of the critical slip circle for factor safety is equal to 1 may be limited by 2 factors. The depth of the stratum in which the sliding can occur, the possible distance from the toe of the rupture surface to the toe of the slope. So, this is indicated in this particular slide after Taylor 1948. Depth factor d by h is given and stability number Cr by gamma h, which is shown here, and here 2 cases. Case 1, use full lines, n value from dashed lines. So, this n value is nothing but n times h. If n is equal to 0, it passes through the toe of the slope. That is a case which actually arises for a case where here d by h is equal to 1. That means that at this point beyond beta greater than 53, it passes through the toe of the slope. And this is case 2, use dotted lines which are shown here. These are the lines which should be used for reading these slides. So, here case 2, then in that case this is the height h and this is the height h which is shown, and this is the d. So, for example, by knowing d by h and beta, ns and n can be obtained from this chart. Say for example, for d by h is equal to 1, beta greater than 53, n is equal to 0, that is d by h is equal to 1, beta greater than 53, n is equal to 0. So, this if you extend, this extent goes like this. Say for d by h is equal to 2 and phi is d by h is equal to 2 and this inclination beta is equal to 15 degrees, you can say this n value will be about 0.65 and the stability number is 0.15. So, this is how we have to read this these charts, and then with this we can actually use these charts for calculating and solving the problems. In the due course of this lecture, we will look into this, how we can use these charts. So, some important points to summarize for the Taylor's method are: it is necessary to ignore the possibility of the tension cracks, otherwise geometrically similar failure surface do not occur on slopes having different heights. So, Hc as because is a function of C and gamma and is not proportional to height h. So, it is necessary to ignore the possibility of tension cracks, otherwise geometrically similar failure surface do not occur on slopes having different heights. Taylor's stability numbers were determined from an analysis of total stress only. That has to be remembered for undrained condition and total stress only. Though it is used for some attempts have been made for using for effective stress, but in such situations it leads to the serious errors. In such situations, Taylor's method is practically recommended or restricted to problems involving undrained saturated clays, or is much common cases where the pore pressures is much common cases are to much common cases where the pore pressures is everywhere 0. Now, let us look in the previous case in the circular arc analysis. These clays when they tend to crack, and then suppose in the process if they get filled up with water, and they can influence the factor of safety. For example, in this particular figure, a critical slip surface is shown here, and this is the depth of the crack. The depth of the tension crack can be determined by Z0 is equal to 2 Cu by gamma, where Cu is the cohesion of undrained cohesion of the soil, and this is the tension crack. So, in this case, if this tension crack is filled with water, this exerts a pressure Pw, and if L is the vertical distance of location of Pw horizontally from the center of rotation, then this can exert a moment to the about this point to a center of rotation. So, factor of safety is resisting moment, that is Cu into L into AC. We need to consider in this zone the weight of the soil and the extension of this portion of the failure surface has to be ignored. So, ignore this soil in the stability calculations, and also this length of the arc extending this portion also should be ignored. That means that after knowing the depth of the tension crack, pointing it on the surface, once your circle is located, slip surface is located, you need to find out the actual length which is involved. So, that is given by, if A and C is here and LAC is the length of the arc, Cu into LAC into R divided by W into D, this portion, that is weight of this this particular portion excluding this small portion, plus half gamma W Z naught square is the water pressure acting at this particular point, the center per meter length or per unit length into L. So, that gives the resting the driving moment. So, the driving moment due to water filled in the crack. So, factor of safety is obtained is given here. So, let us look on the similar the example whatever we have discussed, how we can solve. Example 1, a cutting 10 meter deep with sides sloping at 8:5 is to be made in a clay having a mean undrained shear strength of 50 kilopascals and bulk unit weight of 19 kilonewton per meter cube. Determine the factor of safety under immediate undrained conditions against failure on the rupture surface shown in figure. This figure is shown in the next slide. If the lower 6 meter of the slope is submerged and if there is no external water pressure on the face of the slope. So, in this case, a cross section, this is the figure for example 1. So, a cross section of the slope inclination is shown here, 8 horizontal and 5 vertical, and W is the water table is here, and the water is located here as well as here. Suppose if there is a water which is located at both the sides, then the water pressure effect will the moment due to water here and here will get nullified. What we need to consider this portion as the submerged weight of the soil, that is gamma sat minus gamma W has to be considered. Here this portion, if this gamma sat prevails here, then this is the weight of the soil above the water table has to be considered. And if there is a if there is a tension crack and if this gets filled with water, then the water pressure water exerts a pressure here. So, from here with the depth ZC is equal to 3.5 meters, that is determined, and W is equal to 40.4, this is the area into 1 meter, that is the per meter width of the section of this figure, into 19 kilonewton per meter cube is the unit weight of the soil, yields to 769 kilonewtons, and which is located at a distance of 10.2 meters from the center of rotation O. R is the 16.5 meters, and remaining portion, which is W dash is equal to 140.8 meter square, is the area below the external water level, into this is nothing but a submerged unit weight, which yields to 1290 kilonewton per meter width of the section, which is shown in this figure. Then PW is the pressure due to water which is filled in the tension crack, that is 55 kilonewton per meter. Now, by solving, solution for the example 1 works out like this: factor of safety, resting moment divided by driving moment. The driving moments are calculated, which yields factor of safety 1.85. Now, with no water pressure on the face of the slope, that means that assume that now there is no water on the face of the slope, that means that the unit weight is no longer submerged and it is only a saturated unit weight equal to 19 kilonewton per meter cube. So, with that what will happen, the W dash now changes to W1 and W1 dash, that works out to be 140.8 into 19 is equal to 2680. Substituting here we get the factor of safety of which is less than 1.35. So, the presence of water, which actually if the water is existing on both the sides and increases the safety. But in case if there is a fluctuations in the water table, that means that sudden drawdown conditions or sudden these conditions can affect the factor of safety. A slope of 12 meter, another example, which is a slope 12 meter high has a slope inclination of 50 degrees. Undrained shear strength tests on soil indicate that cohesion is 24 kilopascals and friction angle is 15 degrees. The unit weight of the soil is 17.3 kg per meter cube. What is the factor of safety in regard to cohesion only? So, this is based on the Taylor stability chart. So, in the previous few slides back, we have given for phi u is equal to 0 soils. For C and phi soils also, Taylor 1948 has given Taylor stability charts. So, which are given for Taylor stability charts for total stress analysis are indicated here, where for C and phi soils, in this case, so you can also see that for slope inclination beyond 53 degrees is independent of the d by h, and you can see here this portion, and these curves are for the different friction angles, phi is equal to 5 degrees, phi is equal to 10 degrees, 15 degrees, 20 degrees and 25 degrees. So, dh is equal to infinity here, and this is phi is equal to 0, that is toe failure, and phi is equal to 0, this is in this zone the base failure occurs. Now, by using this chart, for beta is equal to 50 degrees and phi is equal to 15 degrees. So, beta is equal to 50 degrees and phi is equal to 15 degrees, we can get Taylor stability number as Ns is equal to 0.095. So, this 0.095 is obtained here from this chart. So, factor of safety is equal to C divided by gamma h Ns. Ns is the stability number, which is obtained as 0.095 based on the given data. So, 24 divided by 17.3 into 12 into 0.095, which yields factor of safety 1.2. That is what we are required to determine in this problem. What is the factor of safety in regard to cohesion only? So, the maximum height H max, which is critical height, is 1.2 times the height of the h is this actual height which is given in the data. So, once this 15 meter reaches, that means that the slope attains a factor of safety, that is the critical height. Since stability number is equal to C by gamma h max. Now, consider another example, example 3. What inclination is required where a slope 10 meter high is to be constructed and must possess a factor of safety of 1.25. So, this factor of safety is applied to both C and phi. The soil properties are gamma is equal to 16.5 kilo per meter cube, C is equal to 16.8 kilonewton per meter square, and phi is equal to 10 degrees. So, solution for example 3 works out like this. Stability number in the similar way can be worked out, C divided by gamma h into Fs, where 16.8 divided by 16.5 into 10 into 1.25, the factor of safety which is given as 1.25 from both from the cohesion and friction angle point of view, which yields a stability number 0.082. So, the friction angle after allowing for factor of safety is friction angle divided by factor of safety, which is equal to 1.25, which is about 8 degrees. So, now having known stability number 0.082 and pie chart 8 degrees, now you can get the slope inclination as 28 degrees. So, from this chart again the same chart which is shown here, for Ns is equal to 0.082 and pie chart is equal to 8 degrees, we can calculate the slope inclination. So, somewhere around here 0.082 and 8 degrees, the 28 phi beta is equal to 28 degrees can be obtained with the base failure, which is shown here. Now, we have discussed some methods, and in the next lecture we will be discussing about the remaining methods of the which are there for finite slopes. So, before that we look into how water flowing through a slope can endanger the stability of a particular slope, particular section. So, here in this particular slide, failure of slope due to groundwater flow is shown. So, here when the water or a groundwater slips through a slope, this is the natural how the groundwater seeps to the slope. So, this causes a slope failure, like soil slope fails by slumping and endanger the stability the structures which are within the vicinity of the structure. So, this is the original cross sectional slope, and then this as it is unstable, it tends to adjust to a unstable, a stable configuration. So, in order to arrive that, it undergoes this particular soil mass undergoes a movement and fades. So, this is a failed portion which is shown here schematically. Suppose with the remedial measure in the retaining wall, then this exerts can be used for retaining the soil. But what is this influence on the stability of a slope can be seen through physical model. So, which is shown from the as a demonstration experiment. When the water flows to the soil, how it can endanger the stability of a slope. So, in this section, as you see, a physical model demonstration of failure of a slope due to groundwater flow, which is carried out IIT Bombay is shown. As the water reaches the toe, you can see that the slope attains failure. So, this is the formation of tension cracks. This soil is equivalent to a silty sand and having a height equivalent to 7.2 meters and constructed with silty sand which is moist compacted, and the slope is having an inclination of 63.4 degrees. So, let us look into the details again. In this case, a typical slope failure is shown here, a physical model here. This is after University of Bochum, Germany, where you can see a typical slope failure and the formation of cracks. These are tension cracks, and this is a typical slip surface which is formed in a homogeneous clayey soil. And you can see that this portion here is subjected to heaving, where you can see that the heaving portion of this particular soil, the stretch or extent of these failures can be felt up to structures up to this particular portion here. So, this is a physical model which is shown at the end of the test. So, this is the initial cross section of the slope, and after failure it is actually at this particular point, and what you are seeing, these are the marker grids to identify these things enable to identify the failure surfaces. Now, having discussed now, and if you remember now, there are the two stress parameters which are coming into picture. One is short term stress parameter, other one is the long term stress parameters. So, these are referred as in soil mechanics as for long term conditions they are effective stress parameters, and for short term conditions they are total stress parameters. So, when to adopt these things, they depend upon the short term stability conditions and long term stability conditions. The short term stability conditions, basically this is valid for low permeability soil, that is example in clays. At the end of the construction, the soil is almost still undrained, hence the total stress analysis is making use of undrained shear strength is adopted. In case of low permeability soil, the clays, at the end of the construction, the soil is almost still undrained, hence the total stress analysis making use of the undrained shear strength Cu is adopted. In case of free draining materials, that is sands and gravels, drainage takes place immediately, hence the effective stress parameters C dash and phi dash are used. If the material is a free draining type, then the drainage takes place immediately, hence the effective strength parameters C dash and phi dash are used. So, even for the short term stability conditions also, if the material is say sand and gravel, then we use C dash and phi dash. In case if the material is low permeable, as the drainage will not occur, so the total stress analysis is used for the purpose of the analysis. For the long term conditions, after a relatively long period of time, the fully drained stage would have been reached, hence the effective stress parameters C dash and phi dash are used. So, after relatively long period of time, the fully drained stage would have reached, hence the effective strength parameters C dash and phi dash are used. So, in the next lecture, we look into how these C dash and phi dash and C and phi total stress parameters and effective stress parameters can be considered, and we also look into the remaining methods of the analysis, like we have this the Bishop's method of slices and Fellner's method of slices, and other methods we will discuss, and we look into the merits and demerits of these methods for the finite slopes analysis, and we also look into some example problems in using these methods. So, in this lecture what we try to understand is that we try to understand about an analysis of the infinite slope stability, and we discussed about the different cases for a cohesionless soil slope with dry condition and completely saturated condition. That means that water is seeping parallel to the slope surface, and the case where C5 soil with the saturated case, and we discussed that in case of C5 soil the depth is critical height, there will be a certain depth, and that depth is actually referred as a critical depth, which is determined, and we also discussed it based on tau sigma plots about the stable conditions and unstable conditions. Thereafter, we introduced methods for stability analysis of finite slopes. Basically, we looked for undrained conditions, that is basically for short term stability considerations. In this short term stability, we have looked into circular arc analysis, that is phi u is equal to 0 analysis, and secondly we also looked into the method called Taylor's stability method, and then we solved some couple of problems where how these charts can be used, like phi u is equal to 0 soils, 0 soil chart, and or for C5 soils the chart which is proposed by Taylor 1948, that is Taylor stability number versus slope angle for different friction angles. So, based on this will enable us to understand this stability analysis of slopes.